Good morning. Advent of Code again, day 12. And this one's passage pathing. With your submarine's subterraneous subsystems subsisting suboptimally, the only way you're getting out of this cave anytime soon is by finding a path yourself. Not just a path. The only way to know if you found the best path is to find all of them. Okay. Fortunately, the sensors are still mostly working, and so you build a rough map of the remaining caves, your puzzle input. For example, so this is an edge list on the graph. This is a list of how all of the caves are connected. You start in the cave named Start, and your destination is the cave named End. An entry like BD means that cave B is connected to cave D. That is, you can move between them. So the above cave system looks roughly like this. Your goal is to find the number of distinct paths that start at start, end at end, and don't visit small caves more than once. So does that mean an individual path must not visit a small cave more than once? That sounds like... Oh. Okay, well, let's keep going. There are two types of caves. Big caves, written in uppercase, like capital A, and small caves, written in lowercase, like lowercase b. It would be a waste of time to visit any small cave more than once, but big caves are large enough that it might be worth visiting them multiple times. So, all paths you find... I think the postman's here. So, all paths you find should visit small caves at most once, and can visit big caves any number of times. Given these rules, there are 10 paths through this example cave system. Interesting. So the small caves, once we've visited them, we mark them so that we no longer visit them on the same path. The large caves we can visit as many times as we like. So, actually, I wonder if it would be worth restating the graph such that instead of having large caves actually be considered edges at all, points at all, like if B can go to capital A, if there's an edge between lowercase b and capital A, an edge between lowercase b and lowercase c, an edge between capital A and End, then we just say that there's a direct path between each pair of B, C and End. Maybe it's not worth it, maybe it's easier to just leave it as it is. Each line in the above list corresponds to a single path. The caves visited by that path are listed in the order they are visited and separated by commas. Note that in this cave system, cave D is never visited by any path. To do so, cave B would need to be visited twice, okay? Yeah, larger example. So some of the cave names can be more than one letter, even if it's not end or start. Okay. How many paths through this cave system are there that visit small caves at most once? Right, silent contemplation time. Assuming that starts working. Yeah. Well, we'll start by reading in the edge list. So I think what I'll do is turn them from strings into numbers, because numbers are easier to work with. And the way we'll do that is by making a hash table to map the names to IDs. So this will be, what are we going to call them? Nodes. Actually, maybe we'll do this differently. No. So we know that we want to get rid of the new line character, and we also want to get rid of the dash, and then start is L, so we want to add an edge from L to P plus 1. So L points to the start of the line. If the line is like ABC to XYZ, then ABC to XYZ slash N. This one will replace the slash N with a 0 so that it's the end of the string. This one finds the pointer to the dash and then we replace it with 0. So then L points to the A character, which ends here, and P points to the end of this, so P plus 1 points to the X and ends here. So then we add an edge between those two. So these are taking strings. And we use a growable array for the edge list. So vertex 1 is, well, we call them nodes, not vertices. So node 1 is node S1, node 2 is node S2, and then push onto edges N1, N2, and we'll push onto the edges of N2, N1. How did I do this before? Is it htget kv? So if R is an entry in the hash table, if we have it, then we'll just return the ID. Otherwise, we haven't already seen this name, so we put into nodes copy of S, mapping to next node, and then return next node S plus. And also so that should load the edge list into memory, and now let's try and print it out. It might be good if I named the edges so that I could match it to the input. Okay, what we'll do instead of this, we'll walk over the hash table. What's it called? Nodes. And what does this take? Key and value. Let's see what that does. Nope, that's not good. Let's just make sure that I'm using HT walk and go walk correctly. Callback key value, that's correct. Yeah, that just calls CV value. Okay, so they're both correct. Start is node 0. They look like they might be ASCII characters. Why is it going to so many wrong things though? End is node 3. Start A, B, end. Yeah, that makes sense. A is node 1, yep. So it looks like the hash table apply is working, but there's something wrong with the edge list. Well, that looks correct. How bizarre. Where does it get all these edges from? Oh, it's not this. Yeah, okay. Right, okay, that was the problem there. Actually, maybe we'll just we'll leave that as it is. And that way we can look up from a node ID to a node name. And here we can go to node name I. Now hopefully that should correctly read the input. This also wants to be get edges B. And where did I write next ode? actually that while loop is kind of unnecessary. We can always just grr push a single grr new, and we'll know that it will stay in sync, because that's the only place that we ever increment next node. Well, it's almost there. I think I've done the same thing again. Yes, so that's fine. It's because I've put edges v instead of grr get edges v. So I'm satisfied now that we're reading the input correctly and building our thing. And now what we want to know is how many unique paths are there from start to end that only visit lowercase names once. So, yeah. So, how do we do that then? So I don't have an actual queue. What I'm going to do is something I saw in one of Charlie's programs, is I'm going to use the growable array as if it were a queue, but instead of shifting something off the front each time, I'm just going to increment the index at which I'm grabbing the thing from the front. So I'll just slowly waste all of the memory at the front of the queue, but it's better than very quickly wasting all the time spent to shuffle things down in the absence of a decent data structure. So n is get q pop plus plus, where pop is where we're, well, let's call it shift. So n is now the node we're exploring. Actually, I don't think we need a queue at all, do we? Because we're not looking for the shortest path, we're looking for all of the paths. So let's make visited a global. And then we'll just depth first search. So then for each unvisited neighbour of n1, number of paths from n1 to n2 sum up. So instead of find paths, we'll call this count paths, and this will just be count paths from node start to node end. I'd like to use grarr walk for this, but where I put a function, where I say grarr walk get edges of n1 func n, this func n isn't actually a closure. It's just funny syntax for making a function in the global scope. So it can't access the locals here because I don't have any closures. So I'm going to have to not do it that way. So for each edge of n1, sum equals sum plus count paths. Well, if we've already visited n1, then there are no paths through here. Sum equals sum plus count paths of get so edge is n1 I to n2. Well, that seems quite simple. It seems like I've made it look more complicated than it is. I confused myself in the comment. For each unvisited neighbour of n1, the number of paths from n1 to n2 is the sum of the number of paths from that neighbour. Well, the other way around. The number of paths from n1 to n2 is the sum of the number of paths from each unvisited neighbour of n1 to n2. Oh. We only want to check visited if it's a small cave. So if is small n1 and it's been visited, then we have no paths. Oh, and also we've got no base case on the recursion. Ugh. So if n1 equals n2, then there is exactly one path. Not sure if we want to do the visited check first. I'm guessing not. Also, we should memoise this. Oh, we can't because visited will be different. Okay, well, let's just go with that. So this should tell us there's exactly one path. Good. Shall I just run it on the real input and see what it says? Okay. Firstly, I suspect the answer might be a big int. Secondly, I think my comment about wanting to memoise the count paths function may be correct. But I can't immediately see what's the best way to do that, because the set of points we visited could be different every time. Oh, okay. Let's submit that and see what it says. Okay, not too bad. Ah, interesting. After reviewing the available paths, you realize you might have time to visit a single small cave twice. Specifically, big caves can be visited any number of times, a single small cave can be visited at most twice, and the remaining small caves can be visited at most once. However, the cave's names start and end can only be visited exactly once each. Once you leave the start cave, you may not return to it. And once you reach the end cave, the path must end immediately. Now the 36 possible paths through the first example above are these. The slightly larger example above now has 103 paths through it, and the even larger example now has 3,509 paths through it. Given these new rules, how many paths through this cave system are there? So we'll need to know which is the start node and which is the end node, so that we don't visit them twice. And I think this will prevent us visiting the end node twice anyway, but we'll just not visit we'll just do that. If the node we're about to move to is the start node, then we just won't. Now, instead of setting this to 1, we'll set ++. Instead of setting it to 0, we'll set -, and we'll need to keep track of, have we seen any node twice? So if it's small and we've already visited it, whoops, and we visited any twice, then we don't visit it. Otherwise we increase it. And if it's now 2, then any twice is 1. And down here, if it's 2, then any twice is 0. And that should be all. I'll get rid of this incorrect comment as well. Lol, I wrote end n equals node start instead of node end, but I didn't use end n in the end anyway, so it doesn't matter. Well, off it goes. Oh, haha, interesting. Well, I'm guessing I gave a function the wrong number of arguments somewhere. I didn't add any function calls, did I? We don't need this. Very curious. I wonder if it overflowed the stack. Is it lib head dice? Yeah, so let's make that bigger. And actually, I can't remember if I commented out a line that I no longer want commented out. If it crashes again, then I think we'll run it on a small input and see what happens. Oh, it crashed again. Interesting. So that suggests it's probably not the stack. So I now have a way to delete lots of lines at once. Check it out. And they're gone. What did the problem statement say? I said 36, I just saw it. Now the 36 possible pass through the first example above. So it's got the wrong answer, and it crashes on large inputs. Wow, interesting. So it crashes on large inputs. So that does sound like it's overflowing the stack. What the hell? Don't know what's gone wrong there. Right. We could keep track of the for avoidance of doubt, the stack pointer is stored in the very top address, FFFF. Oh, we only want to put any twice if is small n1. So that's why I got the wrong answer on the small sample input. Good, that's the right answer now. $103. That is not the right answer, but at least it didn't crash. Well, at least it's not saying anything about the stack, so it looks like the stack probably wasn't overflowing. So I wonder why it was crashing before, but it's not crashing. I wonder if it was the thing from the other day where I said the computer might be too hot, but maybe that's not the problem. Maybe I just have some subtle kernel bug that sometimes reads the program off the disk and gets it wrong. It is suspicious that it only seems to happen in the programs that I'm immediately working on. So maybe the compiler sometimes gives wrong output. Next time I encounter the problem, I should take a copy of the executable that's wrong, or the executable that triggers the problem, and then build it again and then see if there's any differences. Well, maybe I'll just stop this since it got the wrong answer on the second sample anyway. I might reset this and have a look at the sample 2 problem. So it definitely says the larger example. Oh, there's an even larger example. Oh, so 103 was correct. Okay, we'll make it faster. So this function is what we want, and we'll have. So grarr base gives us the address of the base of the actual array. So we'll save a bunch of function calls if we do this. So then that wants to be so that'll be a bit better. And comment that out. And Boolean logic operators don't actually short circuit, so this is the best way to do a bunch of conjunctions. Yeah, maybe it doesn't make a lot of difference though. Whatever. And then okay. That's not that, that's get edges. Anyway. Feels like it's not going to have made a substantial difference. Also, since n2 is the same every time, we could just look for it going to end n instead of n2. Good, that's the right answer. And it does seem to be a bit faster, I think. Maybe I was just more patient. Well, this is exciting, isn't it? One problem is that we are almost certainly duplicating loads of work because we haven't memoized the count paths function. But it's not obvious whether memoizing it would be a win overall, because we'd also need, so the key by which we memoize would have to be the node we're starting at. Okay, the node we're ending at is always the same, so we can ignore that. The visited set, and oh well, that's it. The node we're currently at and the set of nodes we visited, including their count. So if we visited one twice, it would need to be there twice. So we could put the return values in a hash table. But how many elements would it have and how much memory would it take? It's not completely clear. Well, sample 3 had 3,509 paths, which means at the bottom of the call tree there were 3,509 calls to count paths. So obviously there are more than that going up the tree, but if we say that each one of them takes up, well, how big is the visited set? What's the easiest way to represent the visited set? 1 bit per edge plus enough bits to say which one we visited twice. How many edges are there? I can't remember how many lines of input it said there were, but not actually that many. So it's not that many bits to represent the visited set. Maybe it would be worth doing. Or maybe we could just do it a really stupid way that takes loads of memory for each element and use a jest cache. Well, I'm going to go and make another cup of tea while this thinks about what it's doing. And if it's finished by the time I get back, then I'll submit the answer. And if not, then I might look at memoizing count paths. Well, no, it's still going. What's the plan then? It's so frustrating because I know that if I reset it, it may be mere seconds away from completing. Well, instead of resetting it now, I'll do some silent contemplation on how to make it faster, and then when I open my eyes, maybe it will have completed. Okay, yeah, fine. I've never written a jest cache on SCAMP before. So for those who don't know, a jest cache is kind of a joke caching scheme where instead of having any actual logic on when to evict something from the cache, as soon as the cache becomes too full, you just clear out the entire thing. So you still get some benefit from it, and you don't have to do any thinking at all about what the cache eviction logic should be. So what I'm going to do is I wonder if I wrap this in another function. Okay, so the first thing, the easy thing first, is we make count paths only take one argument. And it always goes to the end node, which is end, not start. So n2 is end n. And given how long it was taking, I think the answer might be a big int. So we'll do the thing where we increment a non-big int almost all of the time, and only when it gets big enough do we add it to the big int. So that will save the number of big add operations by a factor of 30,000, if you follow me. I think I did this on a previous day on camera, but maybe I just did it on my own. I think I've already got it called start n, haven't I? Not that it makes a lot of difference. And then okay, that will count up the number of paths without having to return it. So we don't need sum. And instead of not equals, we can use minus. Not equals is worse because all it does is subtract one from the other and then update the answer to be a literal 1 if it's anything other than 0. But we don't actually care if it's a literal 1 or if it's just 0 or not. So a subtraction on its own is fine. And now the memoization thing. So as well as the visited map thing, we'll have a visited list, which is if we're not returning, we will go, what did I call it? Visited list. Visited list mVisited ++ equals n1. And when we return mVisited -. Oh. Yeah, we can't do it like this because memoizing it won't work. So we actually do need to be returning the number we've visited. Darn, what a blunder. The reason returning it is annoying is because if it's a big int, then we need to deal with where we're going to allocate and free the big ints. And this one's to return. Should we just cross our fingers and hope it's not a big int? I think we'll do that. So if n1 equals n, then we just return 1. We'll print it unsigned though, just so we get a little bit extra. Now the memoization. Well, what if it's known to be 0? If it's known to be 0, then there can't be a lot of work to do, so we'll just say we don't care. So set known needs to make a hash of the visited list and the current node. And put it in the memo table. So how do we make the key? We'll just do this a stupid way. This feels like it might end up slower than the okay, I've got an idea actually. So visited list. If we say that's 1, then what we'll do is we'll set visited list 0 to n plus 1, and if whenever we put something in visited list, we set its number plus 1. And what that will do is we'll then be able to treat visited list as a string. Yeah, this is going to work. So we want and then visited list n visited is 0, and then visited list is just our string that is the key for the hash table. So we'll strut up visited list. Wow, that's neat. Okay, cool. And then set known, we're going to do wow, yeah, this is going to work really well actually. In fact, if we always put it to sum plus 1, and then in known, oh no, whatever. Okay, and then in known we want key of n if we want a free k, we want to return r. So actually, this bit where we strut up visited list and then free it isn't necessary. What we'll do is, when we insert it, we'll strut up key of n, and this will just return visited list. So we can return htget memo visited list. No. Key of n. Now, if memo has too many elements in it, then we want to clear it out. Maybe we will just run it and see if it runs out of memory. I expect it will. Since we have no way to notice that we've stored a 0, there's no point storing a 0. I wonder if there would actually be a lot of zeros to store. Yeah, so what we'll do is, when we set something known, we'll set it to 1 more than what we mean, which is kind of an ugly hack. So when we set known, we'll set sum plus 1. And then where can we return 0? So when we set known 1, what we're meaning is the answer is 0, because when we get something out of known, we subtract 1. Ugh. Disgusting, right? What can you do? So yeah, let's run that and then see if it runs out of memory. I expect it will. So we've got, it will run out of memory. The answer will be too big for 16 bits. Actually, we don't need the 8K stack, do we? Because we determined it probably wasn't overflowing the stack. So we can reclaim some of that. Maybe SLC should have an argument that lets you set the stack size. That's what it was originally. Oops. The memory fragmentation in this program might end up really bad. So we might run out of memory much earlier than we expect, because the hash table doubles in size whenever it gets above 50%, 75%, I can't remember. But whenever it's so full, it allocates a new one that's twice as large. Okay, well, that looks good. But we're also allocating copies of visited list all the time, every time we add something. So what we'll have is like the smallest size hash table, and then a bunch of copies of the visited list, and then when it needs to grow this one, the bigger one will come here, but then we'll put in more copies of visited list, and then an even bigger one will come here, and then there'll be more copies of visited list. So although we'll have like loads of increasingly large chunks of memory free, none of them will be big enough to put the new size hash table in. Although maybe we'll end up putting visited list back in there. Maybe it'll be okay. Right, we need to put a JS cache on this thing then. So how do we know? How do we know how many things we put in a hash table? I don't actually think it has a way to tell you. Maybe it does. HT used. Well, how many things do we reckon we can put in this hash table? Let's say well, let's say 2,000. Who knows? So if there's more than 2,000, then what we want to do is free every element, free every string that we've put in it, and then free the hash table itself, and then make a new one. I expect it will still run out of memory, but then we can drop 2,000 down. Well, I don't know how long I've been talking to myself with no video on, but my computer ran out of disk space again. And this time I didn't notice. So the video stopped recording, but I think it's going again now. So I think we're expecting this to run out of memory. So yeah, if you missed a bunch, I've got no idea what you missed. So let's make this smaller, maybe 1,500. Maybe that won't make any difference. Maybe we'll make it 1,000. Yeah, I was wondering if freeing the hash table and reinitializing it is actually the best thing to do. What we would instead want to do is just memoise the 1,000 positions deepest in the tree. So we could do that we could just not insert something into the table if the visited list is too short. And then once there's 1,000 elements in it, we just never insert anything again. What we can do instead of the jest cache strategy, what we'll do is we'll only allow things to go into the hash table if the value is sufficiently large, because that way we'll know that it represents a large amount of calls to count paths. Right, well, I think we might stop that then and try and make it a little bit better. So the first thing is we won't bother putting anything in unless the sum is greater than, I don't know, 20. And when we free the hash table and then allocate a new one, we can actually do better. We could just zero out the hash table, but I'm going to have to look at how it's implemented to know how to do that. Because what that does is it frees all the memory we've allocated for the big hash table that we're getting rid of, and then allocates a new small one, which is going to have to grow a bunch of times until we free it. So I wonder if I already have a function that will clear it out. I don't think so. What would clearing it out look like? So ht2 is malloc64, so we just set that to 0. So we want to memset ht2 to 0, ht0 plus ht0. ht0 tells us the size. So to zero it out, we just memset memo2 to 0, memo0 plus memo0. And then we save the freeing and mallocing of the hash table. Okay, and is 1000 a sensible value? At what point does it get resized? If it's 75% full, it gets resized. And it gets resized to powers of 2. So we want to clear it out just before it gets resized. So if HTU's memo is 1000, then the size of the thing must be 2048. So if we make it instead resize at 1500, then the hash table itself will still be the same size, but we'll get more visited lists, so it may run out of memory still. Also, I wonder if there can be large call trees where the resulting sum is really low. So maybe this isn't such a good idea, but let's try it and see what happens. Oh, I wrote a bug there. When we zero out the hash table, we also need to set the number of elements used back to 0. is this actually slower than it was without any of the memoization? That would be a good test to do, wouldn't it? It may be that the memoization is so expensive that it negates all its benefit. I actually think that is slower than it was without the memoization. So I counted to about 60 or 70 seconds while that was going on. So if we just comment out the memoization calls and it finishes in less than a minute, then the thing to do is just get rid of the memoization, run it on the real input and walk away until it's finished. So let's leave it at that, I think. There's some more that... Oh, also the visited list needs to be sorted. Ugh, so all that memoization was a big waste of time because the visited list wasn't sorted. Yes. So this will go faster now. But what we should do instead is copy the visited list and sort it. Ah, that's annoying because the method of using the visited list as a string was quite a good saving in the total amount of work on this thing. So what we want to do is that'll be alright, and then return sorted list. And then this no longer wants to strut up. That doesn't want to strut up. And this one wants to right, let's see. So what this memoization gets us is that all the copies of computing the same path over and over again we no longer have to do. However, for every call that, well, for every single call to count paths, we need to sort the visited list and turn it into a string. Or, well, we need to take a copy of the visited list and sort it. So is it going to be better? Hard to say. The problem might be that in general, obviously, memorizing the function is a win, but I just don't have enough memory to have enough memoized results stored. So although memorizing it would be better, if you can only memorize 1,500 different states, then maybe the cost isn't worth it. Well, that's not the right answer now. Did I forget to subtract 1? If we always return 0 from here, then we've disabled the memoization. Maybe I would have had the answer already if I had just not done all this memoization stuff and left the program running this whole time. Maybe I need to build a second SCAMP, and then I can leave the program running on one while I work on a faster version on the other. And then if the first one finishes before I've finished making the second one work, then we're laughing. Because surely just being able to visit one small cave twice isn't going to make it that much larger, is it? Well, actually, let's see if we can work out how much larger it makes it from the sample data. Oh, there are 10. The small one went from 10 to something. The next one had 19, and the last one had 226. And what did they have in problem 2? 10 changed to 36, so that got 3.6 times as big. 19 changed to 103, and 226 changed to 3,509. And my answer for part 1 was about 3,000. So what is this? It's not as bad as squared, assuming these caves were representative. So the memoization is making us get the wrong answer. So it's not as bad as squared, but it does seem to be more than linear, because 36 is 3.6 times 10. 3.6 times 19 isn't as many as 103. And 3.6 times 226 is nowhere near as many as 3,509. It's roughly to the power of 1.5. So that would be 160k for my one, which is a big int, which means my program wasn't going to work anyway. Right, okay, well, if it's actually going to be 160k, then I think what we do is get rid of the memoization, write it as tight as we can, and leave it running for a long time. So let's just copy that to there. So we don't want memoization, we don't want a visited list. No memoization. No, it's not. So what we'll do is we'll do the big int thing. We don't want a sum either. So is there anything else in here that's obviously needlessly expensive? What we could do is grarr base is that plus no, I can't remember. Let's leave it at that and see how long it takes. Well, that is faster than the memoized version. However, my part 1 answer was 13 times bigger than sample 3's part 1 answer. 13 to the power 1.5 is 47. So I think it's expected to take about half an hour. So oh well, let's just run it and then go away for half an hour. See you in a bit. Well, it finished. It only took just over 20 minutes and it got the right answer, so great success. All that time I spent working on the memoise version was a big waste of time. Was there anything I wanted to clean up in here? I can't remember. I read on the subreddit while I was waiting for this to run that somebody else did the thing that I talked about at the start, where you basically remove all of the large caves and then make paths between the small caves. However, he pointed out, or this person pointed out, that if you've got small cave A and then big cave B and small cave C, and you turn that into a line from small cave A to small cave C, and then you've also got big cave D, which is connected to both, then if you just remove that one and make sure there's an edge from A to C, then you'll think there's only one way to get from A to C, even though there's two. So in addition to removing the big edges and adding edges for them, you need to make sure that you know there's more than one path. However, I've just remembered with the way I did the edge lists, you'd get that for free. Although it's better to count the number of edges rather than explore it once for every edge. Anyway. Yeah, so quite a simple program in the end. It only took 20 minutes to run, so if I'd have just left it running, I would have been finished a lot sooner. And we had that problem again where the program crashes every time you run it, and then I recompile it and then it's fine. So I don't think that can be a hardware problem. I think that must be a compiler problem. Either a kernel problem or a compiler problem. But I don't know. Anyway, thanks for watching. Goodbye.